It is my pleasure to invite Professor Anirban Pathak, a distinguished theoretical physicist and head of Department of Physics and Material Sciences and Engineering at JIIT Noida, to the stage. Please join me in welcoming him as he presents his work on the exciting advancements in quantum technologies.
Good afternoon, everyone. I was supposed to speak on morning at 11:40 and I think I'm also hungry and you are also hungry, so I don't want to speak a lot of difficult things. And as things were getting delayed and I was changing my slide accordingly, so that with a hungry situation, you should not have much pressure on the stomach. So you can stop me in between, and as the audience is very harried, so there will be something for everyone, and probably you cannot follow every slide. So some cases I will be fast and just show that what kind of things we do without describing much, and in some cases I'll elaborate and make some comments. So even before I proceed, I just want to make a few comments. Like, since this conference title is also a bit fast and wide, incorporating different fields. So in quantum also, we do a kind of machine learning. Often it's called quantum machine learning, but we prefer to call it quantum assisted machine learning. So what we do, and all the algorithms which you come across often, like variational quantum algorithms, PQE, QAOA. So it's primarily quantum assisted algorithm. So quantum part gives a kind of assistance, or quantum classical hybrid algorithm. So as nomenclature, those things are better than saying it just a quantum machine learning. So we have analogs, like you have a state vector machines, I have a quantum state vector machines. But when you actually implement, you use classical resources also. At the moment, the biggest problem is that, suppose you are doing a variational quantum algorithm, and certain part you have answer, which is a circuit which works on a quantum computer. By the time quantum computer gives results, you have to optimize the circuit in a classical machine. And when the output comes from the classical machine, your quantum computer is off. So a big problem is to put a HPC and a quantum computer nearby with a high-speed line to do something like that, HPC quantum computer integrations. But when we use free machines, like Usha was telling in the morning, that the choice was dominated by what is available for free from IBM. So then we don't have that luxury. So most of the things we run on C-quasm and quasm and such things, and these are just a simulation in classical machines, so you don't see any time advantage there because the machine is just in classical. But anyway, I don't want to talk much about this quantum computing things. I want to talk about something else. So this guy is, so you look at the title. The title is Photons and Quantum Technologies. So I'm not talking about photonic quantum technology, which Vijay has already spoken. So I have to talk about photons and quantum technology. So at the top, this man is E.C.G. Sudarshan, who is one of the most respected Indian scientists, and he was no more, but he is the father of quantum optics. He designed how to define quantum optics, and Wolf Dirac introduced the notion of photon, and the coherent state was introduced and by Glauber, and it's often called the P representation as Glauber-Sudarshan representation, although but without going to history. So now this is the quantum technology. So quantum technologies, mostly there are three facets, and these three are three particles of our national quantum mission also. So one is quantum sensing or quantum metrology, one is quantum computation, and one is quantum communication. The question is, which of this can be done with photon? So believe me, all of this can be done with photon. But in quantum communication, only photonic qubits are used, because your qubits have to fly. You have to go from one place to other place in communication, and your superconducting qubits or ion traps cannot fly. Ion trap qubits cannot fly. So this is only, the third one, quantum communication, is only photon. But quantum computation can be done with NMR, ion trap, superconductivity, many such alternatives. But photonic quantum computer is also an alternative. Initially, people thought that photons cannot be an alternative because photons will fly, they will not remain in one place. There are other disadvantages, that it will not be programmable. You want to apply optics as a gate, now you want to apply another gate, you need to change the hardware. So what is the difference with the usual photonic quantum computer and the superconducting quantum computer? The programming part, like you do in classical computer, you have a software where you are changing the inputs. So in superconducting quantum computer, the hardware is fixed. You are changing the pulses. The pulses which you will say, those are different. But basic hardware is not changed, and the expectation was that photonic quantum computer will not be programmable. So what changes are small steps towards that. We'll come to that. But now the other advantage of photonic, but these are disadvantage. Advantage of photonic computer is that it can work in room temperature. You don't have to go to microkelvin or millikelvin. High precision measurements, there are many possibilities of quantum sensing, and photons are always used. But before we go to these things, first thing I want to note that so-called photonics is a bad name. So all the people who say that we do photonics means are traditionally used to say they don't need photon. So they need classical light, means even solution of Maxwell's equation was fine for fiber optic communication and such thing. So it was a wrongly given name to photonics. So only with the advent of these quantum technologies, photonics is getting its actual meaning, that I need photons now. So here is a cartoon, just because you are waiting for lunch, so you have to make it light. So this guy is saying that I'm light, and the girl is saying that I'm matter. So after so many years of interaction, I don't understand you. So it's all about matter-field interaction. There is nothing other than matter and field, and what you need to understand is matter-field interaction. So she is saying that if you want to understand me, you have to be quantized, as our relationship is quantum optical. So this defines what is quantum optics. So quantum optics is those phenomena which requires quantization of light. Whatever is taught in your school text, college text, like photoelectric effect, Compton effect, these does not require necessarily the idea of photon. You can explain that with semi-classical optics also. So there are things which need photon as essential things, and so photon is a very confusing thing. So I mentioned that my talk's title is Photon and Quantum Technologies. So photon, not photonic quantum technologies. So photon was introduced by G.H. Lewis, a chemist, something like an atom. He did not perspect what are now thought as photon. The idea somehow matured with Planck while he was trying to black body radiation, and Einstein when he was trying to explain photoelectric effect. But then after 50 years, Einstein is saying that after 50 years of conscious brooding have brought me no closer to the answer to the question, what are light quanta? Of course, today every rascal thinks he knows the answer, but he is mistaken. So Einstein introduced it used it in 1905, and then 1951 he is writing this. Then there is a lamp. Everybody is familiar with the lamp shift. He wrote an article, Anti-Photon, and he tried to tell that only a comedy of errors and historical accidents led to its popularity among physicists and optical scientists. I admit that the word is short and convenient to its use, and he demanded that he will give a license. Anybody who wants to use the word photon must have a license, like a driving license. So photon is very complicated. So then we are interested to use that thing with that. And there are many fundamental issues associated with photon. So in quantum mechanics class you have been told that you can write a wave function xix, and mod ix square is the probability of getting it there. Now photon has a very definite momentum, h nu by c. So if the momentum is very definite, there is no uncertainty in momentum. Then position uncertainty is infinite. When position uncertainty is infinite, mod ix square kind of interpretation fails. So you cannot write wave function for a photon in position space. So, but we want to talk about something non-classical states. And non-classical states are very essential. So those which cannot have no classical analog. But Sudarshan give a mathematical treatment. And then this is the approach which we take optically. So there are many of the gates are realized in photonic quantum computing in this way. That there are n of photons, so these photons I will not use for any computation further. So I will measure them, and it depends on the click of the detector whether I get it as a C0 or not. So these gates are probabilistic. So this was a criticism for photonic quantum computing, but this kind of structure was present in quantum optics. So this is from one of our old PRA paper, where we were doing hole bonding or making a finite dimensional state. So this is another aspect. This is called quantum state engineering. So you need a state, you are preparing that state. So what is the state quantum cryptographer need most? I need a Fock state K1. So there is only one photon, there is no superposition with anything else. So that's a non-classical state. Why it is non-classical? So it says that you can write any state of light, a superposition of Fock state 0, Fock state 1, Fock state 2 till Fock state infinity. If you can create a hole that one of this probability does not exist, then it is non-classical. Non-classical states don't have any classical analog. So if you want to get any quantum advantage, you must have a non-classical state. You must have a non-classical feature. Otherwise, if it is a classical analog, you should do that classically. Now, this is something which we have a big group. So this is not my result, this is primarily result from C.M. Chandrasekhar's lab in IISc. So together, one partner is CDAC also, CDAC Bangalore. Henry will be probably in the evening session. So with Henry's team, SETS, Chennai, and we want to make in National Quantum Mission a photonic quantum computer. But in contrast to what Vijay was presenting, Vijay's structures are integrated optics. Our thing will be bulk optics. So we want to go for integrated optics at the later stage, but first we want to develop the expertise, test things, and so now I'll show you something interesting. So this QHQ is called, this is a quarter wave plate, this is a half wave plate, and this is a quarter wave plate. Now you can put the light in the optic axis at different angle. So putting the optic axis in different angle, you can create any arbitrary qubit which you want to create. So now it looks like it can be made programmable. So the now program will be in something else, and that will change the axis of the QHQ. And so at the moment it is done by hand, but if you can control with another program, a classical computer where you will write the program, that will orient QHQ. So my hardware will have only QHQ. Hardware is not changed, the angle in the hardware is changed, and then for different tasks we'll have different things. So now this diagram shows a Mach-Zehnder interferometer, and as it continues you will see that everything, and this kind of structure you everywhere you see. So if it is written BS, it's just a beam splitter, and when it is written PBS, PBS is a polarization beam splitter. It allows horizontal light to move and vertical light to reflect. So these are very common tool in photonic quantum computing or photonic tasks. But here we are showing that. So just controlling this QHQ, you give different angles. So the first optic axis is at 0 degree, 45 degree, 0 degree, you get not gate. It is the same hardware, you change the angle and you get sigma y, sigma z, etc. So, and this is the Mach-Zehnder interferometer. I'll come back to this. Now, with this things, what is done in the lab? So this is a 6 qubit system. But interestingly, 6 qubit does not mean 6 particles. So we have 2 particles, but 6 qubit. So Vijay was telling that photon has many things. So photon has different degrees of freedom. A photon can be polarized. At the same time, the photon can be in different paths. So how this structure works? So this is a part in which we are creating an entangled state. And this fiber controllers are also like QHQ. This is the fiber coupler. This kind of triangle is called retroreflector. So any light which comes, it returns back at 90 degree in the, say, 180 degree opposite. It's in the parallel but in the opposite direction. Now, PBS is one which sends the horizontal light and reflects the vertical light. So this up to this is a normal entangled state, polarization entangled state, HP, VH. Now it comes, and now the normal beam splitter will make it this path or that path, and the PBS will make it a horizontal vertical. So this side we have a 3 qubit unit, this side we have a 3 qubit unit. So now you see that we are writing S2 and 1 0. So these has 2 kind of qubit. So 2 kind of things. One is the path degree of freedom and one is the polarization degree of freedom. So these are single particle, but they effectively work like a 3 qubit system. And what is implemented? So this kind of gates are implemented. So these are polarizing beam splitter, QHQ, and we implement this circuit. So this circuit is equivalent to this. This is the 3 qubit unit. So this is a Toffoli gate. What is Toffoli? Everybody is familiar with CNOT. Toffoli is control not. So if the first 2 are 1, then the third will be 0. And you see, these qubits are not the same type of qubit. Some of them are path in qubit in the path degree of freedom, some are polarization degree of freedom. So you just understand that if you have any arbitrary polarized states and you send through a PBS, so part of it will be reflected, part of it will be transmitted. So it will be alpha kth plus beta kV. So this is a polarization encoding of the qubit. But if you just have a simple beam splitter and you send a single photon, it will be either reflected or transmitted after measurement, but and quantum mechanics tells that it is in superposition. So with certain probability it is in reflected path, certain probability is in transmitted path. So this is in path, this is a qubit in the path degree of freedom. Now you mix it. You put a PBS followed by the BS or PBS followed by BS, you will have entanglement in path degree and those are things called hyperentangled states. So we have implemented hyperentangled states and now we come to Mento. So I'm coming back again to Sudarshan and Sudarshan introduce the notion of non-classicality. So the notion of non-classicality is seen from something called P function. That's at the heart of quantum optics. So much of the photonic quantum computing you can understand without understanding any of these things. Because most of the things which you are doing is digital or discrete variable. But there are cryptography which is continuous variable. So to understand the continuous variable thing, you need to understand these features. So here what we are doing, so Usha Devi introduced the notion of mixed system. So if you can write, and this gate alpha is a coherent state. Coherent state is a classical state, so closest to classical in the sense that they are the minimum uncertainty state. So if you can write a state as a superposition of coherent state and then P alpha or mixture of a coherent states. So alpha 1, alpha 2, alpha 3 and then different values of P alpha and all P alpha are positive, then it is called a classical state. So coherent states and its mixed states of coherent states are classical. If there exists a state in which probability interpretation of P alpha fails, then we call it a non-classical state. So that kind of resource is needed. So bare states are non-classical, entangled states are non-classical, squeeze states are non-classical, and they are my resources. So for photonic things, you need non-classicality as a resource. So here we introduce some squeeze coherent state. So what is a squeeze coherent state means? I was expecting a board. So for a coherent state, the uncertainty in x quadrature and x dot quadrature are same. But if you can reduce the noise in one quadrature, then you can have, at the cost of increase in noise in the other quadrature, without violating Heisenberg uncertainty principle, you can have better sensor. So that's what is done in the gravitational wave detection. So this is our example of quantum sensing. So you can do several quantum sensing or quantum technologies with photon, but you need some kind of non-classicality. And a very good useful thing is squeeze states. Not only that, squeeze states are used in continuous variable quantum cryptography. So we wrote several papers, and this is continuous variable B92 quantum key distribution protocol. And then there's something called Wigner function. So if P is negative, a state is non-classical. But P cannot be determined in an experiment. But Wigner is relatively easier in the sense you can do some kind of tomography and then do radon transform and get the Wigner. There is a tool for playing. Zandu has a tool called strawberryfields.ai. So students can try, there are tools for developing quantum state. Wigner function for quantum state. So this is for the vacuum state, this is for Wigner function for Fock state 1. So this is what I need in an ideal single photon source. So ideal single photon source will have things like this, but what we end up getting is a superposition of this thing. Now, assume that you have an ideal single photon source. Then this is how BB84 protocol works. So BB84 is the simplest protocol. This is in our lab, but it's a model. So you have an optical bench. Then you send horizontal, anti-diagonal, diagonal, all these photons, mix it. Now how, every time you read the protocol, it's told that Alice sends it randomly. So this shows that how Alice sets randomly 0, 1 and plus minus a state. And then Bob measures it randomly. So by now, from this talk, you learned that much optics that you can appreciate how Bob measures it randomly. So Bob use, so here is a beam splitter. So the photon is either here or here. So initial in both, but in the measurement it will collapse in this side or this side. So if it is in this side, then there is a PBS. So if it is horizontal, it will go here. If it is vertical, it will come here. So if this detector click, I know it is horizontal. So this, but one of the detector will only click. So this is the horizontal vertical basis measurement. But if it goes in this side, I have a wave plate. So wave plate rotates it by 45 degree. So if it was 45 degree, it has become 0. If it was 135 degree, it has become 90. So now 90 will reflect 0 will go here. So if this clicks, then I know it was 45 degree polarized. If this clicks, I know that. So looking at the click, I know. So this is how Bob does a random measurement. Now, where from this security come? This security come from our inability to perform measurement in non-orthogonal measurement of non-orthogonal states or conjugate coding. Now, even if you think it simply, so how this photonic technology is used for large scale project. So this photo become very famous. This is a Chinese video conference with Austria, and here is a satellite. So actually, the communication is not, so it's often I heard this kind of words, quantum satellite. The satellite has nothing to do with quantum. The satellite is a traditional classical satellite which just carries a payload, and that payload is capable of doing quantum communication. So as we are showing. So what happens that when the key satellite goes over China, it creates a key. So let's call it key China or key 1. When it is over Austria, it creates key 2 and XOR and announce key 1 XOR key 2. Then the guy which has a key 2, he XORs it again. So key 1 XOR key 2 XOR key 2 will give him key 1. And then both parties has key 1 and then they communicate, and in this process, this is a traditional classical communication. Only the key is generated quantum mechanically. So when this communication is shown, the satellite is no way connected. So satellite is just involved in creating the key. Now India is also interested, and much progress is done by ISRO and in the way to make satellite quantum communication. And computing can be done using various platforms, but communication will always be done with photons. So, basic idea of information security: if a key is secure, then the message encoded is secure. So only the satellite's role was till the creating the key using quantum resources. Now, since this conference is computing, we get back to something simple. How you measure a problem is difficult or not. So we actually count steps. So computer scientists will be familiar, but I assume that there are some science graduates who may not be familiar. So think of a very simple example that so algorithm has nothing to do with computer. Algorithm existed much before computer was introduced, and in the very best algorithms like Shor's algorithm, we use a part which was designed by Euler in 300 BC. We use Euler's GCD finding algorithm in Shor's algorithm. Anyway, suppose when you were first taught algorithm, when in school you have been taught how to do addition. So some teacher taught you that write 2 digits, then write 2 digits. The 10th place is below 10th place, 1 place is below 1 place, 100 place is below 100 place, and then you add. So if there is a 3-digit number, you have 3 steps. 4-digit number, you have 4 steps. So then, if there is an n digit, you need n step. So its complexity is of the order of n. If n is million, so its complexity we write as n. Now if you do multiplication, but you see, 2 addition would have involved 2 steps, but multiplication involved 2 into 4, 1 into 4, 3 into 2, 3 into 1, and 3 addition, so 7 steps. So multiplication, at least you see clearly, is more difficult than addition. So our measure is how many steps it involves, and if you can do something with the polynomial number of steps, we see that it can be solved efficiently. And then there are problems which cannot be solved efficiently, but whose solution can be checked efficiently. So they make a bigger class, because you can, so this is the bigger class NP, and on the traditional classical things, then comes another class called BPP. So you have a probabilistic algorithm, you can solve it probabilistically with a bounded error. So corresponding quantum class is called BQP. So BQP class problems are those problems which you can solve using quantum resources with some bounded error probabilistically. So far, all the algorithms that are proposed belongs to this BQP class. Computer science is somewhat like a religion, and many conjectures are believed and they are not provable. So nobody knows whether P is actually equal to NP or not. So are there P is a proper subset of NP or not, but it's believed that P is a proper subset of NP. So similarly, it is believed that quantum computer can solve only problems in the BQP complexity class. If that is the case, and there are problems outside BQP, then you can pick a problem from here, which is outside BQP, and so BQP is this class, this is NP, you take a problem from here, and then develop an algorithm, a cryptographic scheme, that will be secure even when a quantum computer is built, a scalable quantum computer is built. So that's the idea behind PQC, post-quantum cryptography. So those who are interested in developing algorithm and you are young, take the challenge. look for designing algorithm for problems outside BQP complexity class. Try to solve problems. See, you may fail. Means nobody can promise that an algorithm will exist. But if you have to try to design quantum algorithms outside BQP and take. So all the PQC, post-quantum cryptography, is actually a classical cryptography. And the corresponding background mathematical problem is taken from this space. Now, classically all algorithms, all the cryptographic schemes works with based on the complexity of the problem. So for example, factorization of odd biprime is problem, square-free odd biprime. Okay? So then that leads to something called RSA cryptography. Discrete logarithm problem gives Diffie-Hellman. So far what we know that these two can be broken with source algorithm and source vectors. But there are other algorithms. So elliptic curve can be broken, but it does not mean all classical algorithms are broken in the sense that we know corresponding quantum algorithm, that all classical cryptography. So another problem to look at, and for which our National Security Council is very much interested, can we design quantum algorithms for breaking such cryptographic things for which still don't exist a quantum algorithm. So these are inside, not essentially outside BQP. So even if you are trying to design algorithm inside BQP, look for those cryptographic problems which are used for cryptographic applications but for which quantum algorithm is not available. So I skip these things. So let's deviate a bit. So we do a bit on computing, especially on quantum algorithm. So recently we have worked on Majumdar-Ghosh's spin chain model. These are a physics model, and max-cut problem, which is a computer science problem, which is variational quantum algorithm. And the feeling, the know-how, I told you that variational quantum algorithm, as far as you are calculating complexity, it's fine. But when you implement, you don't really get any speed up. Because you are implementing in a systems, part is in quantum computer, part is in classical computer. By the time classical computer solves the problem, quantum computer is switched on. So all the results are actually C-quasm, and if anybody wants to use it immediately, it's not going to be used unless the quantum computer increases in size. And in that sense, these are quantum assisted classical algorithm or quantum classical hybrid algorithm, not fully quantum algorithm. And we use this kind of words in our image processing algorithms also. Then quantum computing, that's always our interest. And now you become lately interested in photonic quantum computer, and it has a modular structure. Like I show you that my 6-qubit system has two 3-qubit thing. And for distributed quantum computing in NISQ era, photonic systems are pretty good. Now we again, by the time before lunch, so this person asked that, I love a quantum girl, that's natural. Every time I observe you, I find you in a new look. And then the girl say that it's quite, that's what you expect. Because every time you measure, it collapses to something else. Now, the teacher, take this as a know-how, and the teacher asked you that, give an example of quantum superposition. And they told that, well, quantum superposition is something like a mermaid. But teacher asked that, but nobody has seen a mermaid. Mermaid is half fish, half girl. Then student answered, well, if you do a measurement, it is girl or fish. But here is the problem. If you do a measurement in girl's fish basis, then it is that. But there is a basis in which mermaid is a basis element. If you do that measurement in that special basis, you will get exactly that. Quantum mechanics is not probabilistic. So quantum mechanics will be probabilistic only when you don't have access to the basis in which the state is prepared. And this is the core of the quantum cryptography. So in quantum cryptography, by hook and crook, I have to make a piece of information missing from Eve. Eve should know less than what Alice and Bob knows or finally get it. So for example, in BV84 protocol, we have prepared randomly in 0, 1 and plus minus basis. If Eve know which qubit was prepared in which basis, Eve should have done in that basis measurement, measure, prepare and send. And nobody will be able to detect Eve. You can detect Eve because Eve does not have the basis information about the spatial basis in which it is. So here is something interesting. So in our setup, we have shown that there is a Mach-Zehnder interferometer. So interferometer is very easy. In first year optics, everybody has been taught that if light comes, And you need young double slit experiment. You need two coherent sources. So from one light you have to create two. So in young double slit there were two slits. But that's not the only way. You can start with a beam splitter. But now these two lights will never meet. So you have to send them back. So if you send them back with a straight mirror, then it's called Michelson interferometer. If the mirrors are like this, they will go and interfere here, it's Mach Zehnder. If the mirrors are placed in such a way that they will come back and interfere here, that will be called Segnac. So it's very easy to understand. Now I have a Mach Zehnder interferometer. If I work with a single photon, quantum interference, in quantum Mach Zehnder interferometer, only one detector clicks. The other one does not click. So one has a constructive interference, the other one has a destructive interference. Now Elizabeth Hedman introduced an idea that you put a bomb here, the bomb may be active or inactive. So if it is an active bomb, then and a photon comes, it will blast. But if it is inactive, then nothing happens. So if nothing happens, then nothing is there, then the D2 clicks. But if there is a bomb, it's like knowing the Huch path information, or a detector. So if you put a detector and the detector does not click, then means light is going from here. So you don't know the wave property. Now you know the practical property. The moment you know the Huch path information, interference is lost. So if you send 100 photons, 50 will go from here, 50 will go from here. Out of those 50, because here is a detector, they don't have wave nature, they are particle now. 25 will go here, 25 will go here. Whenever this 25 clicks, you know that detector is here or 25 active bomb has been detected. So this is counterintuitive. You have never seen a photon, but still you can see the bomb. And you can see me because light comes and returns, but without sending a photon. But now how can you use this as cryptographic thing? So this is a scheme where this side is Alice, this side is Bob. Alice and Bob randomly put some obstacle. If both of them put obstacles, no light goes, no detector clicks. If none of them put, then it's a standard Mach Zehnder interferometer, D2 clicks. If one of them put, then half of those time this one will click. Whenever this one click, they take it as a case, successful case, where I will get a beat value. So what you will do? So then you will choose that. If Alice has put, let's call it 0, if Bob has put it, let's call it 1. Since Alice knows whether she has put it or not, automatically she can conclude that Bob has put it or not. But Eve does not know who has put it. So Eve's ignorance is of 1 beat. So now we want to implement this in our setup. So everything you will see is interferometer. So just look at, this is the Goldenberg-Hedman protocol, which is an orthogonal state-based protocol, and you see that this is just a, I'm not describing it, but you see this is a Mach Zehnder interferometer with a delay. This is an N09 protocol, this is nothing but a Michelson interferometer with some delay. So interferometer play a very crucial role, and a good quality interferometer, and the kind of problems we are facing is many people need to work on developing the indigenous products when you start off. So we bought a table from Hallmark. So that's the only thing in the lab which is from Indian origin. And it's not really as stable as the Newport tables are. But immediately by naked eye you will not be able to understand. When you try to implement interferometers, you will see the difference. So this kind of BB84 protocols we are showing, and always the claim is that these protocols are unconditionally secure, and that's why we propagate for quantum cryptography. But unconditional security means it is not conditioned on the computational problem. It does not mean it is not hackable. So even this can be hacked. So how it can be hacked? It can be hacked by using device imperfections. So here is the simplest hacking strategy. So you make this, and then Eve send the light through a circulator. It has 3 ports. It comes from this port, it goes here. If it comes from here, it goes to 3rd port, and so on. So if this is vertically polarized, through this polarizer 100% light goes and the wavelength changes. This case no light goes, wavelength remains lambda 1. In this case 50% goes, wavelength becomes lambda 2. Some other wavelength. Now you can then use PBS etc. and distribution. So photons have different degree of freedom. If you can by some method you can change in another degree, you can determine. So polarization is not changed, but wavelength is changed. And then you can attack. So now, stopping this attack is very easy. You have to put a circulator here. So another circulator, so if light will come and that will put it in the garbage. It will not allow it to enter. So you can do that for Alice's side, but you cannot do that in Bob's side. Bob's side light will go. So Bob's side can also be attacked. So for what we do, there is very different kind of attacks, hacking strategies. So one is that you send a strong light and make Bob blind. So there is one such strategy is to send photons inside, and it's called Trojan horse attack, and it's returned back. So Trojan horse attack, so from every component some light is returned back. So for Trojan horse attack also, if you want to implement, you see that it also has an interferometric structure. So interferometers are very crucial for understanding any photonic technology or implementing photonic technology. Now how to stop it? You have to put again a circulator in LSS side, so that external light does not enter LSS side. Only light will come out, but nothing will go inside. So you put another cartoon. So here the girl, boy is starting that, I don't trust you. The girl is saying, why? Because you reflect light. The girl is saying, that's why you can see me. But in quantum cryptography, that may be a problem. So he is saying that, but others can also see you. So he's very conservative. He does not want his girlfriend to be seen by anyone else. And so if can also see you, so then get me a circulator. So circulator stops many different kind of errors. So I'm not describing all the hacking strategies, but I just made it that there are several hacking strategies. And a circulator saves many attacks on the source side, but then what about the detector side? So the best thing which you can have is a device-independent cryptography, but for that we are not yet ready. The technology is not there. So the best available things at the moment is measurement device-independent cryptography. So where the measurement devices are, if anybody attacks, there is any error, your cryptographic key will be still secure. So that's a diagram of MPI QKD, and you see what it uses. It uses light, it uses polarizing beam splitter, and you can understand this because you have already described the BB84 things. So this is a kind of Bell measurement. I'll skip this. Now, so in any quantum advantage you need something which has no classical analog. So if there is a classical analog, classically you can do. So we need non-classical states. And I already mentioned that you need squeeze states and such states. And single photon states are anti-bunch, which must satisfy P is negative. But you don't have any technique that you can do P function in the lab. In lab there is no machine which you give you P function. So there are many indirect ways. So we calculate certain momentum, and from that we check that some kind of non-classicality is there or not. So these are the criteria: squeezing, anti-bunching, entanglement criteria. And we use more than one entanglement criteria, because even if one fail, if it one pass, then you know that it is entangled. But if it fail, the criteria may have failed, because these are not both necessary and sufficient. So now, where we do see this non-classical state? So I write several things. In the beginning I mentioned that it's all about matter-field interaction. So ultimately you have to create this entangled state, the sources, squeeze states, and where from it will come from matter-field interaction. So these are optical fiber, sometimes collinear, sometimes co-directional. The lights are going together, sometimes it's coming in opposite directions, and their interaction can lead to squeezing, entanglement, etc. So this is, so previous one was co-directional, this is counter-directional, light is going in different directions. So all these things we have observed entanglement, but these are theoretical work, but many such theories, this is a Raman process, so everybody is familiar with Raman effect, at least by name, and in Raman process different modes can be get entangled. So entanglement can be generated in many ways. So this was an atom-atom BEC, so I kept it keeping only in mind. So in atom-atom BEC, atom-molecule BEC, one can see entanglement. So practically, this is an optical driven cavity. So over the years, we have seen theoretically in many systems. But of course, all these will not give good entanglement in experiment. In experiments, we mostly use SPDC process to generate entanglement, but there are several ways, and entanglement is more common in nature than separability. Separability is a very special case where concurrence has to be 0. If you have write a general states A00 plus B01, C1, 0, D11, then AD minus BC is equal to 0 or AD is equal to BC. It's the condition that concurrence has to be 0, and that's a special case. Most of the time, any system you check, you will get entanglement. So now particle physicists are excited, they're reporting entanglement in many particle physics systems, but that's obvious. You take any system, so physicists know that if you calculate Krebs-Gordon coefficient, after first step, everything will become entangled. All the atomic physicists, wherever you come across singlet states, those are entangled. So entanglement was very common in classroom physics. Only thing that when these were not used for applications, nobody was telling them entanglement, they were just a state. Anyway, so what do we do with this continuous variable states? So here are some glimpses. So continuous variable direct secure quantum communication. We wrote with a intern from Pune. Shikara was a ISA Pune BSMS student, and it ended up with the experiment in which is shown there. So this is the first EV QSDC experiment. So what is QSDC? That in QKD, the way I have shown that first you create a key and then that key is used for communication. So here we are saying that the entire communication will be quantum mechanical in the sense that you will not generate any key prior. And so this is called quantum secure direct communication. So there are protocols. Long did it for discrete variable thing. Our continuous variable thing was the first protocol of QSDC, second protocol of QSDC and first EV QSDC protocol, which was experimented by Paris and Giabatta in Italy. Then we use continuous variable control quantum conference. So the idea of conference is interesting. That there are multiple people like this and all can communicate with each other. So in QKD it's a two-party thing, Alice sends the information and Bob receives. In QSDC it's a direct communication. In quantum dialogue it's both ways. That Alice and Bob both can speak simultaneously. In quantum conference many people can speak simultaneously. So then there is a control version of that. So that's the most generic quantum communication scheme. So there is a controller. When controller allows, then only other parties can communicate. Now, if you drop controller, it's become a conference. In conference, if n people can communicate, then 2 people can also communicate. Then it becomes quantum dialogue. Then in quantum dialogue, if you make it that only one person communicate, it becomes QSDC. And if you can communicate anything, you can communicate discrete random numbers, and then it becomes QKD. So, control quantum conference is most generic thing. There are drawings, designs, how to do it in optics. So, and all these things, so far we are talking about is primarily communication. But there are computing tasks which also require security. So nicest example is voting. So in vote you need security, anonymity as well as computation. So there are different kind of voting, and what we do in our case is called binary voting. So binary voting means you have to vote between yes and no and traveling ballot, where in the same ballot everybody votes. So I'll come back to that. But voting can be quantum mechanical and it requires security, verifiability, privacy. And the first voting protocol was designed by Hillary. It works like this. So it's a D-level systems. There is one K and K, and if somebody votes yes, then this K becomes K plus 1. And so one qubit is kept with the controller, and the rest other qubit goes to first voter, second voter, third voter. So if this is the state, so there are 3 voters, and only one of them vote yes, then this will become 102102. And when the come back to the controller, he does a measurement and he will know that how many people have voted yes. So that's a simple protocol. But so we design certain things for quantum anonymous vote veto. So veto is a relatively easier protocol. So in veto, everybody has to agree. If one person disagrees, then it's dropped. So I'll show you some. So these are experimental generation of IBM quantum computer. So this is one of the things which we want to do in photonic implementation in next month. So how it works? So in UN there is a veto, and we just want that veto to be anonymous. So now, if somebody has to veto, if he is not vetoing or opposing the decision, he just does not do anything. That's the identity operation. If you want to veto, he applies this gate 1 0. So what is this T? D is the number of iteration. So suppose there are situations, there are 4 voters. So all 4 of them can veto, 3 of them can veto, 2 of them can veto, 1 of them can veto. So if all of them, so initially this is e to the power I pi, this is 2 to the power 0. So if I pi and 2 people apply e to the power I pi, this will be identity. So you will have no way to distinguish between 2 people vetoed, 4 people vetoed, or no people vetoed. But if you make 1 and 3 will give you an extra phase of pi by 2. So if you start with a state like 0 0 plus 1 1, it will become 0 0 minus 1 1. So the Bell measurement will determine that at least one person is vetoed. But this is the best case when odd number of people vetoed. But what about even number of people vetoed? So you have to run another iteration. So in next iteration, what will you do? It will become pi by 2. So only thing I will not be able to distinguish between whether 0 people have vetoed or 4 people have vetoed. So I have to. So we know that how many iteration has to be done? It is 1 plus log 2 base n. So in a couple of iterations, we can implement veto, and this is what we want to implement now in our system. So I'm not discussing this deviations of different parodies. Now there is something called quantum identity authentication. It's a very interesting thing. So all the quantum cryptographic protocol, we are claiming that they are unconditionally secure. But first Alice has to establish that Alice and Bob, that they're really talking to Alice and Bob. So if somebody can speak like I'm Bob, then whole thing is gone. And this is still done classically. So lately there are some schemes for quantum identity authentication. And again, this is not fully quantum, but the classical part has been reduced. And what we have shown that all the things which I'm discussing, that QPD, QSDC, all this can be converted into schemes of quantum identity authentication. And this is a challenging task to implement. There is no practical implementation of quantum identity authentication. Now, I'll give some examples. At the end, I told that I'll speak a bit about secure quantum computation, like voting. So there's a simple task that two people want to compare their age, or two people want to compare their assets, that I have X amount and I have Y amount, whether these are equal or not. In computer science, this is called post-Cold War problem. So post-Cold War problem, when USA and USSR were fighting that want to destroy off some nuclear weapon, who will destroy how much? So they decide that we will destroy the equal. But if somebody tells that we want to destroy 8, others will tell, oh, your intention is not good. I wanted to destroy 50. But since you are saying 8, so I will destroy 8. So we want to come to a number. So this kind of tasks are called quantum private comparison, which are specifically, but one-sided two-party computation is like this. There is a I and J. And I is given by Alice and Bob gives J, and we compute f of ij. And we have some partners. So Alice knows, Bob learns Fij unambiguously, Alice learns nothing about J, Bob knows nothing about I, except whatever can be computed by Fij. So in two-party scenario, Low has a very strong laser that all these three cannot be satisfied simultaneously. So this stops many of the primitives of cryptography that cannot be done quantum mechanically. For example, when BBA84 protocol came, people thought that every cryptographic problem can be solved unconditionally secure. But there is a problem which is very easy to understand. Most cryptographic problems are very easy to understand and difficult to solve. One problem is called remote coin tossing. So Alice and Bob were husband and wife. They fought and now they don't want to see each other's face. So think about the situation. They don't believe each other's friend. It's not very uncommon. It happens in our society. So no third party can be believed. Now they want to toss a coin and decide who will keep the house or the baby or something. So how they will do? So if Alice tosses the coin and tells that 8 is the outcome, Bob will say that was my bet. If Bob tells the bet first, Alice will tell that, okay, this is not the outcome. Because they don't see it. So now, classically the solution works like this. Toss the coin, put it in a box, lock the box, keep the key with you, send the box to Bob. Bob will send the bet. After receiving the bet, Alice will send the key. Now you see, this is a conditional security. It assumes that when the box reaches, Bob cannot break. So it's a muscular power or computational power. You are putting some conditions on the power of an enemy. Now, can quantum cryptography help? The answer is no. The key is unconditionally secure by BB84, but then Bob knows the key. So in two-party scenario, you cannot solve this problem. So there are problems which you can oblivious transform, bit commitment, which cannot be solved in two-party scenario. So we are interested in this problem. So if I is equal to j, then it will be 1. If I is not equal to j, then it will be 0. So you are comparing the equal amount of assets or not, whether 2 millionaires have equal asset or not. So this is one particular computational problem. Now, this can be done using a very simple task. Assume that controller, it's a three-party scenario because two-party you cannot do. Controller has a bail state. Keeps one particle, say 0, 0 plus 1, 1, keeps the first particle and send the other particle to Bob. Bob applies a Pauli operation. So now we know how to do entangled states. Now we know how to apply Pauli operations by QHQ. So when it goes to Bob, Bob applies it. And a bail states, when it is applied by sigma x, sigma y, sigma z or identity, it remains a bail state. He sends it to Bob2. Bob2 applies another operation and sends back to. So how these operations are applied? If he wants to encode 0, 0, he applies identity 0, 1 as x, 1, 0 as 1, 1 as per as his message. So if both of them have made equal, so all these are inverse of it. Identity times identity is identity, x times x is identity, sigma y times sigma y is identity. So when Bob, after that Charlie will measure, Charlie will get the same bail state. If he receives the same bail state, then they have the same thing. If he receives something else, then, but he does not know how much asset is there, because XX will also give the same thing, YY will also give the same thing. So Charlie will know only I is equal to J or not. So this can be executed with the Bayes states and capability of implementing these things. So this is quantum private comparison. Somebody has done with 6 qubit state a real implementation, but what we are saying that it can be done in 2 qubit system also in the Bayes. So this shows some drawing which we want to do in our lab. So these are simple optics to implement QSDC and quantum dialog with entangled states, and how this can be extended. So controlled quantum secure direct communication can be used for quantum e-commerce. So quantum e-commerce is one in which there is a bank and Charlie is online store, there is Alice the buyer, and Bob is the quantum merchant. And all of them does not need to be quantum mechanical. So now people are interested in semi-quantum solutions. So the end user can be classical. So Alice is classical here, and say Amazon and your bank can be quantum. So all of this does not need to be quantum, and classical users can do a measurement on 0-1 basis or reflect the incoming qubit. So this is another interesting thing. So this kind of networks, so we are talking about photonic technology. QKD is quite developed, already there are commercial solutions, many Indian companies do sell. So now we have to look for quantum network, quantum internet, and for computation also. So I will not describe the protocol, but we just tell that this is an interesting problem. This is a grid network, and 2 and 5 wants to share the entanglement. So we have to do some measurement along this line, and 1 and 6 also wants to share the entanglement. They are not directly entangled, but this line is common. So this is called bottleneck. So can we remove the bottleneck? And this problem is called entanglement routing problem. So how to route the entanglement? So this is and this kind of, since it resembles a butterfly, it's called a butterfly network. So the initial problem was how to do it and with a minimum number of measurements. So now we know the solution, and here we show that with certain kind of measurements, which all involves X measurement, Y measurement, and Z measurement, you can remove the entanglement, remove the problem. So this operation transform it here, and now you can just do this vertex deletion and this vertex deletion. So this 2 and this 2 will be separately entangled. But you cannot do that for more complicated thing in the butterfly-like network. Many other things are done with photon, and something can be do in the lab. In the lab, we implement COW and DPS protocol, and some other small quantum optics experiments. But these are schematic drawing with a better lab one can do. So teleportation is a very common thing which everybody knows. So in teleportation, we teleport a state from Alice to Bob. But there are incidents where you can teleport an operator from Alice to Bob. So it's like a quantum remote control. The state is with Bob, the gate is with Alice. So Alice remotely applied the gate on Bob's. And what kind of gate? So whether Alice knows the gate or not. So depending upon their remote implementation of Hedian or partially unknown quantum operator. So just like in teleportation, if the state is known, then it's called remote state preparation. If the state is not known, then it's called teleportation. So similarly, so these are the tasks which are done with photon. Some are still theoretical, some are complicated to implement at the moment, and some are implemented, and some we show that which we want to implement recently, in recent future. And then these are some other people's paper in which people have implemented variational eigenvalue solver or photonic quantum processor. They solve linear equations, etc. And there is a playing platform. So if you want to play, just go use this tool. So one is, this is my friend Peter Marslin prepared something where you can, just like in Qiskit you do drag and drop. So this is this is from Peter's page. So you can drag and draw and put your optics here and see that what happens. So something similar is now being designed by CDAC. So CDAC Bangalore, this quantum accelerator project will also come up with somewhat similar, but the loop will be different. And once you know, you can play with trial and error without actually having the optics. You will have much better idea and better design. So Zartu has a platform, learn, play, and code. So I advise those who have interest in photonic quantum computing, just use the strawberry fields and let's play. So playing is the best way to learn. And I'll stop.
Computation is the God particle transporting.
Yes, teleportation is possible, but teleportation does not mean that I teleport a particle. I have two electrons entangled. And I have now a new electron, so all the information or wave function of this electron goes to the previously existed electron involved. So small scale, so in Chandru's lab also, we have seen teleportation of a polarization state, like alpha H plus beta V is remaining alpha H plus beta V. But if you expect that teleportation that I can go to America by teleporting, it's not going to happen. But information about an electron, a photon, this kind of teleportation has happened.
And veto, photon, because the variable are 5 variables, because 5 permanent member got the veto power. So that 5 by 1, but when we consider election, I have problem, I got 17 variables,
Yes, that's what I'm saying.
17 candidates, and all millions of people,
I understand your question.
none of the above.
No, so we do what we can do with the available resource. So we have voting protocol, which is theoretically correct, security proof is there, that quantum mechanically you vote, it will be fine. But resources is not there. But in Veto, since the number is small, we can implement it. So this is with the present technology, Veto can be implemented, but there are voting protocol which cannot be implemented. But certain things has already been done. In Geneva, there was a municipal election where the voting was less. So in Geneva, some quantum support was taken in voting. Means ID Quantic sold a solution to them, but for securing the postal ballot. So only the postal ballot part. So where the number is less, there the technology is somewhere there. But for bigger numbers, it's not yet ready. And even in the voting, I told you that what I can do is binary voting, where it's a yes, no in parliament, some decision or something. But for multiple voting, there are protocols, but they are even more difficult to implement.
See, all these generation from computers, efficiency, bias, once is stopped. My progress, I had to go down to, like your strawberry field, other, whatever the laws and things, science, technology, engineers, and it goes above that.
No, if it is, we don't understand our brains that human biasness can be removed or not. So even this large language models have already been biased. So if you ask Google to translate my friend is a doctor and to Hindi and my friend is a nurse in Hindi, so in one case it will translate it masculine, in another case it is feminine. So this is already, the biasness is there. But if it is, you are making an experiment where you read unbiased data, so your random numbers are really random. So when you do a quantum random number generator, they are no way biased, and that you can, that's randomness comes from the theory. But if that is fine for your testing, your model, it's okay. But when there is a conscious person, it may be biased.
See, from analog technology, digitized we using zeros and ones. All the inputs is analog number, then it's zeros and one, on or off to begin with. The matrix, the quantum gate matrix also
Yes.
kind of that 2 by 2 matrix.
Actually 0. We have superposition of 0 and 1 as well. So initially, why we have not done analog computing, I'm not talking about communication, because error correction is very difficult or almost impossible in analog computing. So you have a state which is 0 and this is 1. So if you get it here, you know that in digital that it is 0 which is with error come here. But in analog, how will you do error correction? So when quantum states come like the alpha ket 0 plus beta ket 1, then people thought that alpha beta can have any value, so error correction will not be possible. But lately, with almost there, that time it was shown that error correction is possible. So every error here so it's not the traditional digital thing, but every error here comes to become superposition of or combination of bit flip and fetch flip. So if I can correct bit flip error and fetch flip error, I can correct error here. But it's not just 0 and 1. And that is the superposition which gives me advantage. All the quantum supremacy or all this power of quantum mechanics comes from that superposition.
So can you please shed some light on it?
No, I did not read the but I have not read the paper. Teleportation has happened in ISC Chandru's lab. But it's a small distance, only alpha H plus beta B. Yes. And These kind of things are possible. And nobody, don't expect a ball will be teleported or you will be teleported. That's not going to happen.
Thanks for your questions, and thank you, Professor Pathak, for your enlightening session today. We appreciate your contributions in advancing quantum research. I now kindly request Dr. Manisha Nene to felicitate, sir.